and we calculate the conditional variance here. So all of this conditional x. So because both of our estimators are unbiased, we already know that this collapses to beta hat minus beta times beta hat minus beta prime given x. And yeah, this is for both. And then let's do this for the full S estimator. So this is the expected value, and we already plugged in like this form of full S estimator, where we have the S estimator with respect to the true parameter beta and the error. And then you see we have this beta minus beta thing going on, so we can already write that this is this x prime x inverse x prime u times the times the same x prime x inverse x prime u prime in x, so that we have the expected value of x prime x inverse x prime u prime x prime x inverse. Remember, x prime x inverse is a symmetric matrix, so that the transpose is the same as the matrix. So no transpose sign there needed. And then now, because we calculate the expected the conditional variance, we have the conditional x already, and then we can take out all of the x's, so that we have x prime x inverse x prime conditional expected value of u prime given x prime x inverse, like this. And now this thing here is the variance, or the covariance function, covariance matrix of u, which is omega, right? So in the end, we get x prime x inverse x prime omega x prime x inverse, like this. So this looks like a lot, and this is something we haven't seen before, because before, with our standard assumption, remember this looked like this before the covariance matrix of u, if it's sigma squared I, then we would have x prime x inverse x prime sigma squared I x prime x inverse, and then this the thing that your colleague already said happens, where the sigma squared is a scalar and can be taken before this, so that we get sigma squared x prime x inverse x prime x inverse. We multiply something by its inverse, so that we have this, and then we're just left with sigma squared x prime x inverse. And that's the thing we know as the variance of the S estimator, right? And now the issue is, under this new assumption, where we are allowing the scalaricity of population, this omega is a matrix, so it's stuck there, and the whole matrix doesn't collapse anymore. So the variance of the S estimator under this assumption is now this formula, and that's an important result here. Okay, so variance of the OLS estimator. Now let's do the same thing for the GLS estimator. whole term here, and then multiply by the transpose. So we have the expected value of x prime omega inverse x prime omega inverse u times the transpose, which is u prime, right? So if you just look at this, if we transpose this, then we start from the left, on the right hand side, and we have u transpose times omega inverse transpose, which is just omega inverse, because this is also the it was a covariance matrix, so we know that it's symmetric. If the transpose, the inverse of the symmetric matrix is also symmetric, so again, this omega inverse is symmetric, so transpose is the same. And yeah, so, and then times x, and again times x prime omega inverse x inverse, and the whole thing given x. So, same thing as before, everything that is not constant, that is constant can get out of the expected value, so we have x prime omega inverse x inverse x prime omega inverse, expected value of u prime given x, omega inverse x prime omega inverse x inverse, and then again the same as before. This here is the covariance matrix of u, which is omega, so we plug in omega there. And now we see that here something happens in the middle here, because this we multiply omega by omega inverse, which is the identity matrix, and then we're left with this. And now again we get something similar that we got before. We again multiply x prime, like the x prime omega inverse x, by its inverse. So the last two terms also are the identity matrix, and then we are left with, for the variance of the GLS estimator, we're left with x prime omega inverse x inverse. And at this point you also see why the GLS estimator is constructed in this way, why we know that we need to weight all of our observations by this omega inverse matrix, because in that way this whole term collapses, right? So it's the variance collapses and gets very, very small, right? Because this then here was the necessary part, that we need this thing to be an identity matrix, and also the last term that also becomes the identity matrix, and all of this is because we multiply by this omega inverse in the estimator. Okay. Questions for the calculation of variance and expected value? that part about matrices that you can't really tell, even though this matrix definitely looks a lot larger because we multiply by this whole thing here. Like looks like a lot of matrices, and in the end we're going to see that it's really larger in the matrix sense. Yeah, you can't really tell just by looking at it. Okay, so if there's no question for this calculation, then let's do the next part about the efficiency, which is, yeah, it has an interesting design, and as I said before, I'm going to say it a lot, but like this first part, I would expect you guys to be able to do this, what I just did, right? So this part, calculate expected value of an estimator and its variance. I've expected that you can perform this. What's coming now would take you too much time. I still think it's interesting to see how we can show something like this, but for your and also it's always a good exercise in matrix algebra, just to practice matrix algebra, which helps you then with calculating variance, for example. But this exact thing isn't going to be in the exam because it's just too long. So for the efficiency, but the result is important, right? So that GLS is sufficient under this condition. So the GLS estimator is more efficient, and also it's important that you even know how we show this efficiency, right? So how to do this, like the concept of this is more efficient if the difference between the variances, between the variance covariance matrices, because beta here is always a vector, right? So the difference between the OLS variance covariance matrix and the GLS variance covariance matrix is positive definite. Or semi-positive. I think it's enough. Semi-positive definite would allow the variance to be the same, which they're not always. They're not the same. We know this. So let's focus on positive definite. Thanks. Okay, so let's plug this in. So the question is this thing positive definite? And the exercise sheet gives you one little note on how we do this. We can do this by using that a positive definite matrix can be written as the product of a transpose by itself. Right? So we know that if this is a positive definite matrix, so under the condition that we do have a positive definite matrix, we're going to be able to write this difference here as the product of C prime C. Okay? So sum C prime C. So that's our goal in the end. Okay? And the issue is, first, how do we get this difference into a product? Right? And the way to do this, if you just think about like a different difference. Like, let's say 4 minus 2, right? Just like a very, very easy difference. 4 minus 2. How can we turn this 4 minus 2 into some sort of product? We can factor out the common component of these two, so that we have 2 times 2 minus 1. And then all of a sudden, we have this product here. Like, that's our goal. And we're going to do the same thing with these matrices. We're going to rearrange this so that we can factor out the common component from both terms to have this. And in the end, the interesting thing is that we're going to get this matrix multiplied by its transpose. Okay. So for that, we first have to know what we factor out. And this is, at that point, the first term is going to help us because we already have on both sides of this here a common, like in the first term, we have already have these terms that kind of look very similar, right? So we already have something that is the trend. Right? So we kind of want to factor out something like this. The issue in this is that we are left here with this omega, and yeah, we could maybe keep the omega, but in the end, this is going to look a lot nicer when it's not there. So we need to find a way to also split this omega. And because we know that it's a variance matrix, we know that it's positive, covariance matrix, we know that it's positive definite, we can also write omega in this form. So we're going to do this first. Write omega is a covariance matrix. Which is positive definite. And omega inverse is also positive definite. Because omega is positive definite. Okay, so we can write omega, and I will what exactly I wouldn't be able to come up with this myself. So we say omega is equal to some matrix phi inverse prime times phi inverse. And we know that this is phi prime inverse, right? So because both of them are inverted, we can also factor out this inverse, and then we have phi prime inverse, and from that we already also know that omega inverse is equal to phi prime. And we need this because we somehow need to split up this omega, and then by doing this we also know something about omega inverse, which is in the other term. Okay, so this is kind of what we use. Okay, so this is one. Then we can plug it in so that we have x prime x inverse x prime phi inverse prime phi inverse x prime x inverse minus x prime phi prime x inverse. So we plug in omega and omega inverse into these in their different form. And now we already see that these here W prime. So these are already two inverses. So it kind of makes sense. We split right now this variance matrix of omega that we know is positive definite because it's a variance covariance matrix into this form prime matrix prime matrix, right? And this, just call it W. So the second term we could also we're going to leave it like this for the moment. Okay, so we know that we can factor out so we're going to factor out the first term, so x prime x inverse phi inverse, x prime phi inverse prime. Okay, pull this in front, so left, factor out to the left, which is important for matrices, and then in the middle, we're just left with the identity matrix, and then we factor out on the right hand side phi inverse x prime x inverse, right? So right now I just have factored out, like, produced a larger product from the first term. And the question now is, like right now it just tells us it's just the same as the first term. And the question is, what has to come in here to what is here from the second term, right? So the question is, how, if we factor out this x prime x inverse x prime omega, this phi inverse prime, and the other term on the other side, from the second term, how does it look like? Like, how does the second term have to look like so that this factorization would work out, right? So for that, we need to expand x prime phi prime x inverse, so the variance of omega of the GLS estimator, so that the factorization works. So let's start with phi prime phi x inverse, and think about how this thing needs to look like. So we have to, we want, well, how does expansion work? The same, in the matrix form, the same as always. We remember or we write out something that we usually don't include, which is in this case the identity matrix. So we remember that we can multiply, or this, we can write the product, the matrix also with identity matrix multiplied to both sides of this side, or both sides of this matrix, right? So we multiply by the identity matrix on doesn't do anything because it's just like multiplying by 1. And now we know that the first term of these identity matrices, the first part, has to look like the thing we factored out from the OLS variance. So the first term has to be x prime x inverse x prime phi inverse. And let me write it as the other way around, phi prime inverse. Right? So that's the first part of the identity matrix. Then we multiply again by just what we got before. And on the right hand side, we also, the term on the very right side also has to be what we factored out before. I think which is phi inverse x prime x inverse, right? So let me do this. Okay, so the first part of this I matrix has to be this, and the second part of this I matrix, the last part of this I matrix has to be this. And now the question is, what do we have to multiply these terms by to get the identity matrix? Right? And then we have to think about, well, first thing is, if we multiply phi prime inverse, what we have to multiply to the identity matrix? Well, the matrix itself. Right? So because we have there inverse multiplied by the matrix is the identity matrix. So we expand this, or we multiply it by phi prime. Multiply this by phi prime, and then we're left with x prime x inverse x prime. And if we multiply that by x, then we get x prime x inverse x prime x, right? And that's also given. And on the right hand side, the same thing. What do we have to multiply phi inverse by? The identity matrix, we have to multiply it by phi. And then we're left with x prime x inverse. We have to multiply that by x prime, so that we get x prime x inverse. That's kind of how we build this matrix, how we expand this matrix so that we can then afterwards factor out this term again. This here is the identity matrix, and this is also the identity matrix. So in the end, we didn't actually do anything, we just expanded the matrix. We just multiplied by 1. And the good thing is that now we know that this part in the middle here, because we factor out this x prime x inverse x prime phi prime inverse, and on the right hand side, phi inverse x prime x inverse. We know that this part here in the middle is our little question mark that we're left with. If we factor out. So we can write it out, and we have x prime x inverse x prime phi inverse phi prime inverse times the identity matrix minus phi prime x prime phi prime x inverse x prime phi bracket times phi inverse x multiply a lot of times, like this part here is phi prime x, then we have here an x prime phi, again a phi prime x, and again a phi x prime phi. So again we have products of matrices that are transposed of each other, right? So we can rename them and have like this here called this that, then this x prime phi is the transpose of this, then we multiply it by z, and we have the z prime in the background here. So in the end, this middle matrix here, if you look at it, it's I minus z, z prime, z inverse, z prime. And I hope that you recognize this matrix as a projection matrix, our annihilator matrix, where z would be the variables, right? So this is, and z this is equal to nz, which is a projection matrix. And we know that projection matrices are idempotent. We showed this in the first exercise. Idempotent means that if we multiply this matrix by itself, it's the same matrix again. So we have an idempotent and a symmetric matrix. So if we write this, and then we can also name these terms here. I already called this W prime and this thing here W. So in the end, we can write this very shortly by just W prime and Z W. And because we know that MZ is idempotent and symmetric, we can write this as W prime MZ prime MZ W, and then we see that we again have a matrix multiplied by the transpose, and we are at our goal. Okay? And C prime C is positive definite, which gives us that the difference between the variance of the OLS estimator and the GLS estimator is positive definite, and the conclusion then is that the GLS estimator is more efficient. We swap a lot of matrices in and out. But I think the most relevant part of this exercise is definitely the result that under heteroscedastic and autocorrelated errors, the GLS estimator is more efficient than the OLS estimator. Yeah. And the rest is a lot of if you understand this in the end, I think you are well prepared for the matrix algebra part of the exam. I think it's a good practice to recognize do this one-on-one, because I think, yeah, this is going to be easier for me to show you individually the points that you are actually interested in. Because as I said, this is like not the most important thing, and I also wanted to talk about the homework now, so yeah.
Why is W prime same as the green mark string in the line of the question mark?
No, W prime is not the same thing.
No.
No. That here is W. That's always this W.
Yeah, that's what I meant. So you say this is W prime, right?
Yeah.
The green mark part.
Yeah.
Yeah, that's what I meant.
Yeah.
But because in the line with the question mark, we write x prime I inverse prime, and then later, can you go down? And then later we write x prime phi prime inverse.
That's because it doesn't matter for square matrices if you have the inverse of the transpose, or if you transpose, invert the transpose. Right, so like this is this thing, sorry. That's it. Thanks. Maybe wait, can I write this down? I really find that I introduced this. Phi prime inverse is the same as phi inverse prime. That's good. Okay. So let's have a quick look at the homeworks. And the first part. Okay, so let's go through the exercise very quick, and I'm going to just tell you where like the issues were, because I guess you all looked at it, and most of you also did this correctly, so I don't have to explain to you how this works. But like the couple of small issues here that cost out. Which is actually like, okay, so in this Monte Carlo simulation, you were supposed to have a look at the consistency of the OS estimator. And then the first part, I gave you two data generating processes in the multiple regression form, where you have, in both cases, two variables, x1 and x2. And the difference between them, as all of you recognized, was that in the first part, here, in the first exercise, the covariance between x1 and x2 are zero, so that's the important part here. And then in the second part, we have that the covariance between the two is 0.99, and x1 in both cases has a normal distribution with parameter 0, 2, and the x2 has normal distribution with error 0, 1. The error term E was in both cases supposed to be normally distributed, standard distributed errors, and the true coefficients were given as 2 and 4. Like this. Okay, so I think most of you lost some points in the setup of the term the result of the of most of you, so it didn't matter in the end for your rest result, but like this is the one point that in most cases, one point that you missed is that thing that you did, like also you did something here. And one of the things is that and maybe that was a little bit mean, but but the true model here is actually a model of a constant here. And a lot of you simulated a model of a constant, but estimated the model with a constant. And this is not correct. Okay, so here's no constant, which you did correctly. But the important part that is also true if in the estimation here. At this point, in the estimation, that this should also not have a constant, right? Because you're kind of estimating. You don't estimate the correct model, right? So you misspecify your model in the end. And I mean, that's the nice thing about simulation is that you do know the true model, so you should also estimate without, like, the true model. That's kind of one that happened to a lot of. So, yeah, estimate without constant. And then the next thing, and it's also in the setup, was that I specifically specified the covariance of the two, and a lot of you then calculated the correlation, or no, you set the correlation to 0.99, which is really, really a lot. Like that's like crazy a lot. And then calculated the different covariance, which I just didn't ask. Okay, so that's kind of wrong in that sense, because, and I like the people lost the point, lost it because I wanted to make sure that you know that there's a difference between covariance and correlation, and I specifically set the correlation to the covariance and not the correlation, right? And I can kind of guess why, and some of you did it, but yeah, that wasn't like the point of this exercise. So that's just one of them. Yeah, and because both of these things come up in exercise 1, right? Both those of you who did both only lost 1 point because it's only kicked the point for the exercise for the part 1. Okay, so yeah. So this was the other part. I think for me it's really important that you get that this is like the covariance and the correlation are two different things. So the setup was a little bit different from what I imagined. Another thing, yeah, some of you forgot the economic examples. So in the economic example for those of you who wrote an economic example, I was very, I usually I gave all of the points because they were all fine. I just would hope for a little bit more of an explanation on why this the variables are correlated. Some of you were very, very short. So next time if something like this comes up, maybe discuss it a little bit more on why this happens. And of course, you needed to find some sort of economic example. For those of you who didn't, you needed to find some sort of example where both of the variables were correlated. And one of the easiest examples, I think, is in the production function. We have output on the left-hand side, and then we have capital and labor on the right-hand side. Capital and labor input are usually very highly correlated, and then talk about it a little bit. But just something like this. I also already gave points, we just mentioned something like this. Okay, then the point of this whole exercise is obviously that to show that in the second exercise and discuss it, show me in a plot a graph, explain a graph. Those of you who didn't produce graphs didn't get the point there. And show that in both cases, in both of these data generating processes, the OLS estimator is consistent, so the MSE goes to 0. And in the graphs, you saw that the first data generating process had, from the beginning, a lower mean squared error because they were uncorrelated, and because the covariance is 0, and because the covariance in the second data generating process wasn't 0, that increased the variance a little bit, so it changed the mean squared error. And most of you, and I also saw that the plot, in most of the cases, and I think this is kind of what confused some of you, is that the difference is actually not that big, and that's fine, like in a lot of cases. And I think it's also then a good exercise to see that in some cases, like even though this covariance looks like maybe a lot, and maybe isn't, because that depends on the variance and variances of the two regressors. There's still this, it's still not such a huge issue, right? But it's still there. So in the end, what you could show, let me do this. I think in my plots you see the difference a little bit. You also see it's not like a huge difference. So for the first model, for the data generating process with covariance 0, I get the highest MSE for 10 observations at 0.05 almost, and then the MSE for the second is 0.25. I mean, which is for 10 observations actually a lot, but then you also see that this reduces dramatically, very quickly. Even for 50 observations is already very small, and I think that's kind of where some of the confusion came from, I guess. So you see, this is really only an issue in very small samples. Yeah, it's kind of what you can take from this. But the issue is that, like, in some instances, we do have very small samples, so that's still an important result, right? Okay, then the second part, you actually, like, most of you did all of this correctly, and then in the third data generating process, you all recognize that the issue here was that the first estimator, the first regressor is now not only correlated to, is correlated to the error, so we have the covariance between the x1 and the error of 0.5. That worked out correctly for those of you who did the first part. An economic example, as I said, some of you forgot or didn't write one, or I gave points for that. Again, I would have liked a little bit more explanation. But so I think one of the most common examples, and I think one of the standard examples for this sort of endogeneity, so we have here an endogeneity problem, is in microeconometrics is this ability augmented variable bias, where we cannot observe the ability of a person, but if we talk about the wage of a person, that is, and have data on the education and, I don't know, work as something else, then education is also correlated with the ability of someone, and the ability also influences wages directly and not only through ability. So we get this omission variable bias here. And which leads to endogenate, which leads to an inconsistent estimate. And then what most of you also did correctly was then explain how the mean squared error looks like and what happens there. And I just had this very nice little, I just produced this very nice little plot. You see the pink, yeah, and we discussed this already, that the variance still goes to 0 even if we have this homogeneity problem. So the MSE then in the end is only governed by the bias, but because the bias doesn't go away asymptotically, the MSE stays very high. Right? So that's kind of the argument, and I think also we did all of that, also with this, explain this correctly, that the issue with the inconsistency in the homogeneity problem is the bias and not the variance. And that's kind of the difference between the two. So if we have correlated regressors, we don't have a problem with the bias, but we might have a problem with the variance, especially in small samples. So that's kind of where what was kind of the learning of the homework. Okay. And then just so you understand it, the bars are meant to be the contribution of the bias and the variance to the mean squared error. So you see that the contribution of the variance, which is the dark gray, goes to 0, and the contribution of the bias just stays the same. Because the bias doesn't go. Yeah. I'm not allowed to update this. Did I forget? Did I forget to upload the last week? What did we do last week? Wait, didn't I do this one last week?
Yes.
Yes?
Then
Did it not?
maybe
Stop out?
it was minus.
No, I don't know, maybe, I don't know. Maybe sometimes it doesn't show. So if, yeah, just as a also note there, if you're missing anything in the Blackboard, please write me an email because it happens that I forget things. But this time the professor is against me uploading the results, so I'm sorry. But you can always, I mean, please write me an email if it's unclear how you get, how the grading came to be. Any other question here? Or I hope you guys had a little bit of fun. Maybe one thing I wanted to add also, and I also hope you had a little bit of fun working with R. Please next time read my instructions. A lot of you did, but there are reasons why I want the results as PDF. I can also explain. If you send me a PDF, I'm not going to change it, and both of us are very clear on what you gave me and what I got, and what I'm going to give. In our Markdown files, in Word files, in R files, I can change, like stuff can happen, right? So at some point, maybe I accidentally change something, or something gets needed, I don't know, right? So please make sure you give it to me in the PDF. And also, the solution need to contain the code and the output, and in the best way possible, like in a way where I get the code and then the output, so that I know where things come from, and if your code works, right? So that's kind of one part, and for that, the best thing to do is use our Markdown, because everything else is gets a little bit confusing, and it's really hard to break and to find where you try to tell these stuff. So the instructions are meant for you to provide a sheet of paper that I can grade in give me